In this video, we're going to be talking about inference for beta I. So that's just any of our betas, whether beta naught, which we're really not going to do that much with, or more importantly, our beta 1 through beta k. So these should be relatively easy for us to pick up because they're going to be performed just like well, not just like, but more or less identically to any of the other t-tests that we have done in the course so far, whether we're talking about for a single population mean, for two population means. Those are really the big ones that we've done, but those are going to be similar. We also did some testing for our beta 1 in the last chapter, so it's going to be more or less exactly the same. But let's go ahead and start taking a look. Start off with our hypotheses. If we're looking at a two-tailed test, we're going to see beta I equals our arbitrary constant as our null hypothesis. Beta I does not equal C as our alternative hypothesis. For our one-tailed test, our null will be beta I less than or equal to C for a right-tailed test, and our null hypothesis will be beta I less than or equal, greater than or equal to C for a left-tailed test. And of course, they correspond down here as well. Alternative, beta 1 greater than C for a right-tailed, beta 1 less than C for a left-tailed. All right, then usual difference with our critical values. And when we're looking at a two-tailed test, it's alpha divided by 2 and then the degrees of freedom. If we're doing a one-tailed test, either right or left-tailed, our critical value is T alpha and then our degrees of freedom. Our degrees of freedom are going to be the same, so n minus k minus 1, so that's going to be the same for both of those, as is our test statistic. Go ahead and make more room so we can actually see our test statistic. So our test statistic for one and two-tailed tests is equal to BI minus our arbitrary constant minus C divided by SBI. So S with the subscript BI, that is the standard error for that particular beta, or for that particular B. So BI minus C divided by SBI, standard error, that is our test statistic. Our conclusion criteria, those are going to remain the same as they have been for doing a two-tailed test. If our critical value, if our test statistic falls to the right of the positive critical value or to the left of the negative critical value, then we're going to reject the null hypothesis. So again, just as long as they fall into those rejection regions, and they don't fall in the middle, right? If they don't fall in between the two critical values, then we're going to reject the null hypothesis. For our left-tailed test, if our test statistic is less than the critical value, we will reject the null hypothesis. And for a right-tailed test, if the if the test statistic is greater than the critical value, we'll reject the null hypothesis. So when we are talking about hypothesis testing for betas, really the most important one is a test of significance. Hopefully we're all familiar with what a test of significance is, but that is the most important one. When you're running this stuff through a statistical software package, right? So when you're just when you're going ahead and estimating your regression equation in the output, it's going to go ahead and give you the t-value and so the test statistic and the p-value for tests of significance for all your coefficients. because it is that important. You want to know what is statistically significant, right? What is actually having a non-zero effect on the dependent variable, because if you've got a variable that's not significant, that's telling you that maybe this doesn't have any effect, right? Or it doesn't appear to have any effect based on our data on the dependent variable. We might want to chuck it out of the regression equation, or if we think that there's a sound reason why it should affect the dependent variable, then that's going to give us pause and get us to go and look and see, well, what's causing this to be insignificant, right? But that being said, let's take a look at a t-test, all right? Actually work through a couple of these. And we'll start with a test of significance. So in order to do that, we're going to need some information. So I'm going to rewrite our equation that we've been working with for a while. So here's our equation. So we are going to need to know our coefficients. We're also going to need to know our standard error. So I'm also going to show you one of the ways that we might see that pop up. So when people write out their equations, oftentimes they'll also write out, if they don't have it already in a table, or in some cases, even if they do have it in a table and some output, they'll go ahead and write it with the regression. They'll put kind of SE in parentheses under the dependent variable, and then in parentheses there will be numbers under our coefficients. Whatever it's under, it corresponds with that coefficient. So for example, if we have 2.14 here under negative 11.75, that's telling us that the standard error for B naught is 2.14. The standard error for 2.068, the standard error for our B1 is 0.136. And the standard error for B2 is 0.029. So these are our standard errors. Probably gonna have to erase that just to make room, but we want to go ahead and write down these coefficients, B1, and we're going to want the standard error of B1, B2, and the standard error of B2 as well. Speaking of B2, that's what we're going to focus on, all right? At least for this first test. So the question might be something along the lines of, does an additional year of experience have a statistically significant effect on hourly wage? Right? That's just that's one way of kind of asking for a test of significance. All right. A very simple, straightforward way of asking that is B2 or beta 2 statistically significant? Or we could also kind of put it more into, we're putting it into words, but in less of a statistical mathematical way. Right? Does an additional year of experience have a statistically significant effect on wages? So to answer this question or perform this hypothesis test, we're going to first start by stating our hypothesis. All right, so hopefully by this point we know that a test of significance is a two-tailed test with an arbitrary constant of 0. That's exactly what we have right here. The null hypothesis is that beta 2 equals 0. So we're assuming that experience has no effect on wages. Our alternative is, hey, I think experience probably does have an effect on wages. It's probably a correct assumption, but that's what we're going to try to prove with our data. So then we're going to need our critical value. As I mentioned, this is a t-test, and we're going to do this at the 5% significance level. So if we're doing 5%, alpha is 0.05. This is a two-tailed test. We need to cut that in half. So it's going to be 0.025. And then we will need our degrees of freedom, which we know are n minus k minus 1. And if we don't remember from the previous video, the sample size for this regression was 1,000. Our k is the number of independent variables we have, and we have 2. We have years of education, we have years of experience. And then the 1 is just there, right? So 1,000 minus 2 minus 1 gives us 997. Right, so this is, higher than the degrees of freedom on our chart. We could find the exact one, but it's not going to be much different from 1.960. So we're just going to use the infinite degrees of freedom here and say 1.960. All right, if we are drawing out our distribution, now would probably be a good time to do that. Right, because we've got our critical value and nothing else, so this is a time for us to write that down so we make sure we don't confuse our critical value with our test statistic. Can also help remind us that for a two-tailed test, we should have 2 rejection regions. We should have a rejection region defined by the positive version of our critical value and our negative value. So we have 2 rejection regions, all right, 1 in each tail. Then we will go to calculate our test statistic. All right, so our test statistic is equal to BI, or in this case, B2. We know that B2 is 0.145. Right, minus our arbitrary constant. If you want to put minus 0, you can. You don't have to, but I'm going to do that just for, just because, right? Just so we know that we are technically subtracting something, even if it's 0, which I guess is technically nothing, so disregard that last statement. All right, but 0.145 minus 0, or just 0.145, and then we're going to divide by the standard error. And if we go back and we look, which I'm going to have to do, the standard error is 0.029. So once we have that, we're going to punch that into our calculator. And oddly enough, we're going to get a test statistic of exactly 5, which I find unsettling for some reason, but nothing we can do about it. It is 5, that is what it is, right? So once we get there, we can either just compare our test statistic to our critical value, or if we're drawing out our distribution, look and see where this test statistic falls in relation to our rejection regions. All right, we can see that it falls pretty firmly into the rightmost rejection region, in the right tail. So we would reject the null hypothesis. All right, and I don't really have enough room to write the conclusion, but the conclusion would be, all right, that years of experience has a statistically significant effect on hourly wages. There are a couple of ways you could say that. You could say, reject the null hypothesis, conclude that beta 2 is significant. But if you wanted to put it into a little bit more plain English, reject the null hypothesis, conclude that years of experience does have a statistically significant effect on hourly wages, would probably be the simplest way to put that. All right, but that is a test of significance. Again, these are the most important. These are the ones that you're going to do first if you're actually running a regression, because again, you want to know which of your independent variables actually matter in the model. If they don't matter, you want to take them out, right? Or if you think they matter and it doesn't look like they do according to your results, then you need to dig deeper and see why, right? The ultimate result might be that they don't matter, all right? But there might be some other problem that we're not going to really get into in this course. We'll use to save that for kind of higher level econometrics classes. But it's not just tests of significance. Those aren't the only tests that we might find interesting. We can use this to do tests for anything, all right? Just so we get a second one, I believe I have one. Yep. Another one ready. Let's do a test with our other coefficient, B1. So here we're going to say, again, I'm going to just state it in kind of plainer English. So I guess kind of, well, it doesn't matter. So let's say that we're wondering, you know, does an additional year of education lead to more than a $1.75 increase in wages? So when a question is phrased like that, there are a couple of things that we have to think of, right? We have to think about what it's really saying. So if I'm saying more than 170, all right, 175, that's one indicator. That's giving me a baseline number. But I also have to pay attention to that fact of it's a $1.75 increase in wages, right? So that's telling us, right, it's moving upward and we should get a positive, all right? Our arbitrary constant should be positive. If it was to say decrease, that would change things quite a bit, right? Because if it's a decrease, right, if an increase in your independent variable leads to a decrease in your dependent variable, you'd have to make that negative, right? Your coefficient would be negative, and so you would expect that any proposed or hypothesized values for it are also negative. Regardless, right, this is a more than $1.75 increase in hourly wages. So once again, we're going to start by setting up our null and alternative hypotheses. For our null hypothesis, right? Well, actually, let's take a step back. So I always say that the easiest way to do these is to determine your alternative first, and then I go to class and I do the null first. But the alternative, right, that's what we're trying to prove. What we're trying to prove, or at least show, is that one more year of education leads to more than a $1.75 increase in hourly wages. So we're talking about education. That's the variable tied to beta 1. So we need to have beta 1, and then we're saying that it's more than a $1.75 increase, right? So increase, that's telling us that this is positive. More is telling us, since this is positive, this needs to be greater than, right? So kind of continuing, going past that 175 in a positive direction, right? Once we have that, the null hypothesis is trivial. We just need to make it the opposite of whatever the alternative is. So our null hypothesis will be beta 1 is less than or equal to 175, and our alternative is beta is greater than or not greater than or equal to, just greater than. Beta 1 is greater than 1.75. So we're going to, let's see, what did I do this one at? I did this one at the Yes, I also did this one at the 5% significance level. So when we're setting this up, this is a one-tailed test. We don't need to split alpha in two. All right, alpha is 0.05 if we're doing a 5% significance level. So T 0.05. Then we'll need our degrees of freedom, which once again are n minus k minus 1. That doesn't change. The sample size is still 1,000. The number of independent variables we have is still 2. So our degrees of freedom is going to be 997, just like it was in the last example. Once again, we're just going to use the infinite degrees of freedom to state that, because that's what it's going to be closest to. again, if we are using the distribution, if we're drawing that distribution out, we might want to go ahead and take this time to establish our rejection region. Then we will move on to the test statistic. So our test statistic, once again, right, in the numerator, we're going to have our B, right, whatever B is, B1 in this case, so 2.068, minus our arbitrary constant, which is 1.75. Then we're going to divide by the standard error for our B1. So the standard error of B1, that is 0.136. Once we punch this all into the calculator, we're going to get a final answer of 2.338. All right, once we have that, we can check to see where that falls in relation to our critical value. All right, and that does fall into that rejection region. So since it falls into the rejection region, we're going to reject the null hypothesis, and we're going to conclude that increasing education by a year, right, an additional year of education leads to more than a $1.75 increase in wages. All right, the last thing that we're going to do is we're going to look at calculating confidence intervals. So this is the 100 times 1 minus alpha % confidence interval for beta I. This is going to look pretty similar. We're not going to really mess around with this because we've done confidence intervals. We're not changing a whole lot. So here is the formula. Right, and it's a pretty basic formula as far as confidence intervals go, just because we're condensing a lot of stuff that we're not calculating on our own. But this is what it is. So BI plus or minus T alpha divided by 2 with n minus k minus 1 degrees of freedom times the standard error for the particular B. So let's say we wanted to find the 99% confidence interval for beta 1, is what I put here. All right, so we would start with our BI, in this case B1. So 2.068 plus and minus our critical value. So if we're doing this at the 99% level, our significance level is 1%. Our alpha is 0.01. So when we cut that in half, we're going to get 0.005. Then we're going to have our degrees of freedom. Again, these degrees of freedom haven't changed. 1,000 minus 2 minus 1 is going to give us 997. And then we're going to multiply that by the standard error, which we know is 0.136. All right, the only thing we really need to go and find, since we've already been using these other two, is that critical value, which should be relatively simple. It should be 2.576. Multiply our critical value and our standard error together to get 0.350. All right, again, that product of our critical value and our standard error, that is our margin of error. So here we have a margin of error of 35 cents. All right, the last thing to do is add and subtract our margin of error from our coefficient to get our boundaries. All right, and so we get an interval of 1.718 as our lower bound and 2.418 as our upper bound. If we were to interpret this, we could go with something along the lines of, and I'm going to do some rounding here. I am 99% confident that an additional year of education would lead to between a $1.72 and $2.42 increase in hourly wage. All right, so again, kind of putting that kind of more in plain English. All right, we could also say I am 95%, or excuse me, well, we could say 95, but we would be wrong. I am 99% confident that beta 1 is between 1.718 and 2.418, right? But again, if you are asked to get this information for somebody, the reason they asked you to do this is because you know statistics and maybe better than they do, but even if not, then they still want you to tell them what it means in plain English. So, right, 99% confident that a 1 year increase in education leads to between a $1.72 and $2.42 increase in hourly wages. Right. But that is confidence intervals, really pretty straightforward, very similar to what we've done in previous semesters and throughout this semester as well. All right, that is it for this video. In the next video, we're going to be talking about categorical variables, right? We haven't dealt with those in a while, so let's see if we can bring them back into the fold, and that's what we'll be doing in that next video. So I will see you then.